Hello and welcome. Now it's time to continue my previous Chessbot project. This part, we will inject some machine learning aspect. This machine learning will power the both opponent in our chess game. Oh, right. Before that, in the previous part, actually I forgot to add a pawn formation mechanism. That's why before finishing this part in off-cam, I edit the code for part 1 and update the repository. And now, as you can see, we can do the pawn promotion like this. Okay, back to the part 2. The board in this video will not be final form of this project. It's just a step 1. I plan to keep improving it with various algorithms. For now, I just simply fit the board state to the model and the model will decide what moves should be taken. Okay, let's move on to the code. First, I will show you how my backend evolved from a multiplayer set to single player set. As you can see here, I import thoughts for the machine learning model. After that, here is the function to encode the state of the board to some matrix. The shape of the board is 8 times 8, so I initiate a zeros matrix with the same shape. The next line here is the piece mapping. We decode pawn to 1, rook to 2, knight to 3, bishop to 4, queen to 5, and king to 6. Now, to differentiate between white and black faction, we multiply our white piece with 1 and black with -1. Next is the iteration for the encoding board. Here, we iterate our piece in the board from the chess model and encode them to the zeros matrix we initiate before, and the last part is to return the function with that matrix. The next function here is still same, it's to check with the winner. Below that, here we have two classes. The first class here is residual block class, and the second class here is the module that we will use. The residual block is the basic block for our model here. We will discuss more about this residual block and the model more in the next section about how we train the model. Don't worry, it's still in the same video. Now here is our first real action. The three lines here are to load our trained model. Here we need to state that we want to load the model in CPU because I trained this model in Google Colab and used to the GPU, so in default the model must be loaded in GPU. Sadly, my PC doesn't have NVIDIA GPU, so the only option is to load it into CPU. The next is still same. What changes are here below this command. Here is the section on how we decide the best move for the board. The first step is to list all legal and possible moves. After that, we copy the variable because we will modify some of its aspect, but still need the original one. Here, in the next line, we iterate all legal moves and encode them. Inside the iteration, the important lines are here. This is where we try to encode the board state before and after we take the move. With this now we have two 8 times 8 matrices. We will fit both of these to one model, so we need to merge them, right? That's why here we concat them, so the final shape is 2 times 8 times 8. For all dataset, the shape will be n times 2 times 8 times 8. And here is the variable because in every state, the total legal move we can take can be different. After that, here we take the minimum and maximum from our dataset. So it must be clear that the maximum is 6 and the minimum is -1. No, the minimum is -6. It's because the way we encode our board state. After that, we normalize the dataset so the range is 0 to 1. The next step is converting the dataset from NumPy to torch tensor so we can feed it to the model. After we feed the dataset to the model, we will get rating from 0 to 1. It is for how good the move is. That's why the next step is to find argmax or the index where the max value is. The location of the maximum rating is treated as the base move that will be taken by the bot. Next is to retrieve the base move by using the index we get and put that base move to the dictionary with k move. After that, we return this dictionary as JSON to the front end. Before that, here is in this line, we turn the legal key as true because if all of these moves are successful without problem or checked by some special if to detect an illegal move, then this game is valid. And that is for the backend. Now let's move to the front end. Now the part that we update other than the promotion counting is here. We process the move variable here. Here I try to detect if I found a move with 5 character length. You know, all the moves I use here only have 4 characters. The first 2 characters are for the fish origin location and the second 2 characters are the target location. The move only has 5 characters if there's a pound promotion. So the last character is for E for queen, N for knight, B for bishop, and R for rook. At the end of the pound promotion mechanism, and for all move activity, we push that move to the historical array and write it to the special if that we already prepared first to show the historical move using the write move function here. The historical array move will be sent to the backend so the backend can know the state of the board. You know, HTTP is stateless, so we need to send the history from start to end. We need to retell the story from start to end every time we send the state. Below this is still the step. It's to detect castling move. Next here is the detail of what happened in the write move function when we write the historical move in the special diff. It's a simple operation but quite long because of the nature of JavaScript, you know, so I will not explain them. And that is for the front-end change. And finally, let's move to how we train the model. But before that, let's see how we build the dataset for the model. The code is quite long, but I will make it fast and just explain some important points. So here we use a PGN dataset as the live data. PGN is special format data text that contain the detail of chess match. In this PGN dataset, I have tens of thousands of matches. For every match, it have several metadata, and one of them is the ELO rating. I already googling that a good player has ELO rating above 1,800, and that's why in this code I only include a match with ELO rating above that. If a certain match passes the filter, then next we read the history move in that match and encode the board state during the match using this function getStateBoard. The state of the board will become the feature. In this experiment, the board will play as black, so I only record all black moves as label. Label in this code is binary, which are positive human move and negative human move. If in certain state human use that certain move, then it's labeled as positive human move. Otherwise, negative human move. In this step 1, we consider the human leg move to be the best since it's used by high rating player. After that, we input it directly into training code, right? Well, no. In my off-can experiment, when I do that, the model can convert because there's an imbalanced dataset between positive human move and negative human move. Chess has nearly infinite possible states because it's a very big number, and in that certain state, usually only one move that's considered good among many possible moves. So that's why in this code, I try to balance a dataset with negative on positive level. Because a positive level is minority, then I choose some random row in the negative level with the same total as positive level. So they will have a 50-50 percentage in the dataset. Okay, first I will explain about these two classes. As I said previously, the basic building block of our model here is the residual network. What operation happen in this residual block here overall is like this. Now move to the main model class. Here we use a convolutional model because we want to observe the spatial pattern. As you can see here, actually it's the same as multi-layer perceptron code, but we use a convolutional layer here and a residual network as the basic building block to simplify it. Just imagine we use an ordinary dense layer, but in this code we replace them with this residual network, which consists of convolutional layer and a batch normalization. Usually, people will also use a drop layer to prevent being trapped in local optima, but here I just want to try something new. In a nutshell, a way of drop layer to prevent local optima is to give a little chance to the algorithm so that we can reset the weight in our layer. Reset means to make it the zero value. Here in this code, we initiate the model and load the undersampled dataset. After that, we normalize the dataset, convert it to the torch tensor, and include it in the data loader. The optimizer we use here is Adam. After that, here is the loop for the training model. Because the training takes a very long time to finish, here I include a checkpoint saving mechanism so that in certain interval epochs, the code will save the trained model in that epoch. After that, finally, when the loop is over, we save the final model like this. I already said that I don't train this model on my PC. Instead, I use Google Colab. So I just copy and paste this code to the Google Colab and do a little modification. So I can load the model and dataset in CUDA and change the interval checkpoint from every 10 epochs in the original code to one epoch because looks like it's take a very long time just finish one epoch even after I use Google Colab and CUDA GPU. Because I only have a free Google Colab, so I only have a very limited time to use CUDA for one account. So that's why after I run out my session time, I copy and paste this code to another Google account and run it again. But I modified a little again, so instead of running it from epoch 1, I resume from the last checkpoint. And that is how I trained this Take 1 bot. Now let's see how it performs in the real game. I will play with the bot. Okay, in here I play as white, so I will move first. And I will do this. Okay. Oh, looks like our bot make some stupid mistake. Oh, I think it's yeah, stupid mistake.
win. It's quite easy to win, I think, but yeah, in my next experiment, maybe I will try to improve this board, of course. Okay, that is for the demo.
And that's it. Actually, before this, I'll also try using a ordinary multi-layer perceptron, but the result is not quite good. Because of that, I think the model need to see the spatial correlation or spatial pattern. So that's why I change the model from the multi-layer perceptron to the here residual network. And looks like when I use the residual network, there's a convergence. So I think it's worth then at least than multi-layer perceptron. That's why I use this for this experiment. In the next part, maybe I will try to improve this both using another algorithm, or maybe I will use generative adversarial model. So the model will try to improve it by itself by competing with the another model, the Gen stuff. And I think for now, just that. Thank you. Bye.